Okay, hi and welcome to the examples for the video notes 8.8, which we're talking about exponential functions, specifically exponential growth and decay in a little bit more detail. So we said we're going to do a couple examples here, one exponential growth real world problem or in context, and one for decay as well. So let's read through these. I've marked them up a little bit and we'll work through this together. So it says, since 1985, the daily cost of patient care in community hospitals in the United States has increased about 8.1% per year. And I know I should read the whole problem, but that word right there just throws up a flag. I know from that word that this means that it's an exponential growth. And as soon as I get that, that gives me this inside my head. And so it's what pops in there, right? I start thinking about what's the exponential growth basic formula so that I can start plugging in the values that I recognize. So again, f of t in this case equals our initial value times 1 plus r, 100% of our original, plus r, our percent increase, and that's what that part there, that 8.1 represents, right? That percent increase, which represents my b value overall, right? I'm calculating it as a percent increase as opposed to a whole growth factor. They didn't give it to me that way. All right, so that all streams in my head as soon as I see that part. Now let's finish reading the problem, identify all our information, and we'll see what we come up with. So it says in 1985, such hospital costs were an average of $460 per day. That's as soon as I know this is exponential, I know that there's some amount that we're starting with, and that's kind of what they're telling me here, right? The initial cost or the average cost originally were $460 a day, and it's increasing at 8.1% per year. So I know that that's kind of my starting value or my A, so I would mark that up as my A. It says, first, write an equation to model the hospital care. Now, we know that model really means multiple things. It can mean a table. It can mean a graph. In this case, it does want you to eventually estimate with it. You could use a table and graph here. However, as soon as we're estimating at distant units, especially with an exponential, and this is asking us to estimate, in this case, it's going to be in 15 years in the future. We know exponentials grow crazy fast. So a rule here is going to be your best bet. Doesn't mean you couldn't do all three, but I'm going to take the route of the function rule because at this point I know kind of what's coming. So I kind of pre-thought that a little bit for you. But in general, when they ask you to model, it's always a good thing to have the function rule. You should really probably represent it in all three forms, especially if you're doing a content problem like this. So it says write a model of it. In our terms, we're going to take function rule. And then B, it says use your equation to find the approximate cost in the year 2000. So we know that we're doing that into the future. So we'll address that after. So first part is we're really just going to write a function rule. Visually, we could do a little sketch. We know it's going to increase, and we know our table values should be increasing as well. That's what the growth part gives us. So let's see if we can write down some of our information. I usually always like to start when I do a problem like this where there's a bunch of information, and I like to list the base rule that I'm working with, which you can see I've done here, and then I like to identify all the factors that are contributing to that rule that I can find, and I need to find all of them except one, right? Because we can only solve a function if we have one unknown. So looking at this, we've kind of already identified R. We said that 8.1% is our increase per year. So our R value then, I'm going to write down is 8.1%. However, when we put this into the function, we need to use a decimal. We can't use it as a percent. R isn't calculated as a percent, it's calculated as a decimal. So we need to change 8.1% into a decimal, which is 0.081. If we put 0.81, that's 81%. We wouldn't want to do that. So I've got 0.81. Now, what's my B value then? 1 plus the R, right? That's what B represents. So I'm going to take 1 plus 0.081, which you could have just guessed is 1.081. Super easy to do. So now that I've got that, I can start writing out let's get the rest of my information, then we can start writing in the general form or the function rule for this. Our A value we identified right away was $460 per day. And it's weird that it's per day. Don't worry about that. That you should be able to recognize that that's your initial amount. So I'm going to put down here for my initial amount is $460 per day. Now, the time is something that we don't know yet. They don't give us time when we're making the model. And remember, when you're making a model for this is in terms of a function rule, we want to make sure that that's represented as an input, right? You should have an input and an output for every type of function rule that you have, and t is going to represent our input. So right now we don't know this yet. We're going to find out in b because we can see where it is there, right? Don't know yet. All right, so let's write our model. And so our model is going to look like f of t is going to be equal to our initial amount, 460, times 1 plus r, or 1.081 to the t value. That's our model. Okay, so we've completed part A. That's a function rule that we can use to predict any values of time in the future of how much it's going to cost hospitals if they start out at $460 per day in 1985. So part B then asks us to approximate what it's going to cost in the year 2000, or what it did cost in the year 2000. So to do that, that means that we're going to calculate our t by taking the year 2000 and subtracting 1985. Right? That's going to give us the difference, or how much time change is going to be, and of course that's 15 years. So what are we going to do? Then we're going to take our model that we wrote, and this time we're actually going to evaluate it by plugging 15 in. So f of 15, the function at the value 15, or time of 15 years, is equal to 460 times the growth factor of 1.081 raised to the 15th, which represents 15 time period changes, or 15 years of change. And if you calculate that, you throw it in your calculator, you're going to find out that the average cost of a hospital in the year 2000, based off those requirements, is going to be $1,479.60. And of course, you know that this is a contextual problem, so you're going to go ahead and put that into some type of wording, because you must represent it back in the way that you got it. All right, so let's take a look then at an exponential decay, very similar in the content. So this problem, though, is going to say, since 1980, the number of gallons of whole milk each person in the United States drinks each year has decreased 4.1%. Lots of reasons for that, right? Lots of different flavored drinks, lots of different flavored waters. People are drinking skim milk. I don't know if that counts. It does say whole milk here, so I'm guessing skim milk is a version, or 2% or 0.5%. So that kind of makes sense. Back in the day, like my grandparents would have, they drank whole milk probably from the cows on their farm. But as we moved along, we've changed the way the things that we drink. So that works for my head. But we notice the word decrease. That's the most important part there, which means that we're going to have a decay factor. So initially, I'm going to come down here and write out my function rule. All the information is going to flood into my head. F of t equals a, my initial amount, times 100% of my original minus whatever my rate decrease is. In this case, it's going to be 4.1%, times however many time changes or events have occurred. So let's read on and find the rest of our information. I guess we can write r in there since we found that. Our percent decrease is 4.1%, or let's go ahead and change to the decimal, 0.041 as a decimal. Okay, so in 1980, each person drank an average of 16.5 gallons of whole milk per year. Okay, sounds like a lot, but that is an initial amount, so that's my a value. So I'm going to write that down as 16.5 gallons per year is what that represents for my unit. It says A, just like the last one, write an equation. We're going to go with the function rule again for the gallons of whole milk drunk per person. And then B, use your equation to approximate the consumption of per person of whole milk in the year 2000. So kind of similar in that regard. So let's write our function rule, but we don't have our B yet, so let's identify our B. Our B then is 1 plus 0.041. Or, I'm sorry, did you notice a problem there? We said it was a decay, and I wrote a plus, so this will be a subtraction. So when we subtract that, 1 minus 0.041, we should end with a decimal. Notice I was going to end with something larger than 1, and we know a decay can't do that. It has to be some form of a decimal, less than 1, greater than 0, and so in this case it comes out to be 0.959 is our B value. So let's write our function rule then, C of t, or consumption. I don't know why it's C of t. I used F of t there. Let's change that. We'll match what we've got. So the function in terms of time, that's what that should represent, is, right, our initial value. So 16.5 gallons per year of whole milk times our growth factor. In this case, it's 0.959 raised to the t. And again, t we don't know yet. And when we move to part B, we know that we're starting in the year 1980, and they're asking us to estimate what happens in the year 2000. So we're going to take the year 2000 and subtract 1980 to find the difference. And that's going to equal 20 years. So you can see that we would have plugged that back in. I'm going to change that to an F right there and change that to an F. So the function at 20 years, starting with 16.5 gallons per milk per year per person, with the decay factor of 0.959 after 20 years, you put that in your calculator, you're going to come up with is 7.14 gallons of milk per year. And again, you're going to put that back into some kind of contextual part because it came to you that way. You're going to represent it in the form that you had it. All right. So there's two examples of exponential functions. You should have fully understood and got a great amount of detail on the difference between exponential growth and decay, and how to do a couple contextual problems with them. All right, thanks for watching. We'll see you for some problems in class. All right, have a good day.